So, let us see another application. Under the applications, the third application, let us see. This is the stability of carbocations, B carbanions, and C free radicals. Apart from these three, we have number of other intermediate species, but basically generally the carbocation, carbanion and free radicals are the mostly we find as a intermediate species. So, let us understand how these intermediates are influenced by the inductive effect, the application. So, the first carbocation, let us see. A carbocation essentially will have a positive charge. An example, simplest example for the carbocation is a methyl carbocation, let us take. So, this will have a positively charged. So, either you see the total electrons surrounding, that is 3 into 2, 6 electrons. So, 2 electrons less to the octet. Its own electron of carbon, if you see also 3 electrons, 1 valence electron is deficient. So, ultimately the carbon is found to be electron deficient system. Electron deficient system it is. Such a system, if somebody donates an electron density through the inductive effect, like for example, any alkyl group attached to this type of the carbocation, the positive charge however cannot be totally nullified, because it is not giving the electrons, it is giving electron density. So, therefore, the positive charge what happens is, just like a bulb is glowing, but not with full power, it may become a dull. Like that, the carbocation also, the effective charge of the positive charge will become less. So, the charge will be there, but its power will be less. So, because of this, alkyl group is showing the plus inductive effect. A small electron density, it is pumping through the sigma bond and the carbon receives. So, therefore, the effective positive charge, it is nullified for some extent. Therefore, the positive charge will become dim. So, therefore, the charge itself is instability here. The charge is decreased, therefore, the stability is increased. So, this type of carbocations are found to be more stable. So, whenever such a alkyl containing carbocations, you can call it as a 1 degree or primary carbocations, So, whenever if you take primary carbocation, it is having some stability when compared with only the methyl carbocation. Similarly, when 2 alkyls are there, a carbocation having the 2 alkyl groups and 1 hydrogen is called much more stable. Okay. When compared with this one, it will be much more stable. Just a relative word I am using. It is more stable, it is much more stable. So, because the 2 plus I effects are influencing from the both the sides, so therefore, the effective charge is much more decreased, the problem is decreased. It is called 2 degree or secondary carbocation. Similarly, a carbocation having the 3 alkyls. Whenever 3 alkyls are there, carbocation is much more stabilized. So, it is in fact out of all the 4, so you can put a superlative degree most stable one. Out of these 4 only, however, once again, so the most stable carbocation is 3 degree carbocation, or it is called tertiary carbocation. So, if such a, without mentioning the R nature, if these 4 are given, you say that the 3 degree is more stable than the 2 degree, than the 1 degree, than the only methyl carbocation. So, this is the order of the carbocation stability. So, in general, what is happening here? The carbocation, the positive charge, any charge is a problem for the system. Here this is a positive charge, so therefore, carbon has got some electron deficiency. So, when alkyl groups, they are donating groups. In fact, if there is a chlorine, for example, if a withdrawing group is there, it would have become a destabilized. But fortunately, we have an alkyl group which is donating. So, therefore, positive charge is partly fulfilled. 2 alkyl group, 3 alkyl. So as the alkyl groups are increasing, the positive charge is more and more, the deficiency is fulfilled, so therefore stability it is going on acquiring. So therefore you can write like this. Some examples you can write like this. So ethyl or a ethyl carbocation is more stable than the methyl carbocation, because one methyl is acting as a plus I group. Similarly, N-propyl carbocation and isopropyl, if you take, isopropyl is more stable than the N-propyl. Okay. And tertiary butyl is much more stable than the isopropyl, because here 3 alkyl groups are there, only 2 alkyl. Here number of carbons total system is 3. Again this already discussed in the mines. 2 directly supporting, here 1 directly, 1 indirectly. Therefore isopropyl is more stable. Isopropyl is more stable than the N-propyl. In the third case, this is 4 carbon, this is 3 carbon. So number of carbons are differing. So you can immediately point out, so this is more system. But if the number of carbons are same also, you can say that. For example, this is tertiary butyl and this is a also butyl system, but it's 2 degree butyl. All are butyls, you can say butyl, butyl and another butyl. This is also butyl. So they all are butyls, but it is 3 degree and it is 2 degree, it is 1 degree. So you call this one as a tertiary butyl, this is secondary butyl, this is a primary or N-butyl. The nomenclature itself, secondary butyl, tertiary butyl this is. So tertiary butyl carbocation is more stable than the secondary butyl carbocation, then N-butyl. In all the systems 4 carbons are there, but the carbocation is attached directly with the 3 alkyl groups, 2 alkyl groups, only 1 alkyl, isn't it? So therefore the more the number of alkyl groups attached, more will be the stabilized. In fact, if minus I groups are there, carbocations are destabilized. So the carbocation stability will be like this. The more the alkyl groups are attached, more will be the stability. So let us take the stability of the carbanions, that is C minus stability. Okay, this is a carbanion, anion with carbon, so carbanion it is. So simplest carbanion is a methyl carbanion. Let us study how it is constituted. So the minus charge means 2 electrons here. So this is 3 into 2, 6 electrons plus 2, 8 electrons. That means octet rule, it is fulfilled, there is no excess. But say 1 electron, 1 electron, 1 electron from the bonds, 1 electron of the carbon, and these 2 5. So 5 electrons are there in the valency, that means 1 electron excess, or the negative charge. Evidently it is showing that it has an electron excess system. So therefore it is considered as a electron excess system. So whenever electron excess are there, now we should have a withdrawing groups. Instead of withdrawing, if you have an alkyl groups donating systems, they are destabilized. So like that now the carbon with minus charge without alkyl groups are more stable now. This is more stable. When alkyl group attached to a system, this is less stable because it is destabilized. So already the carbon is having a excess electrons, and the alkyl group is known for the imparting the electron density through the bond. So therefore if all such alkyl groups are donating, the carbanions are described that the more the alkyl groups are, more destabilized. And if you have a 2 alkyl groups there, it is much more destabilized, and if 3 alkyl groups are there, much more destabilized. So it is very less stable, isn't it? Very less stable. However, it donates the electrons very much quickly. So therefore in turn it is also called very strong base. It is very strong base. It is one of the trimethyl, that is tertiary butyl carbanion is found to be a very strong base, because all the alkyls are donating. Originally it has a minus charge and all methyl groups are donating. so were found to be a stronger base. However, stability, if you compare, a carbanion without alkyl group is more stable, one alkyl group less stable, two alkyl group much more stable, much more less stable, and three alkyls much more less stable. So it is reverse to the carbocation. In fact, carbocation is 3 degree, 2 degree, 1 degree. Carbanion is 1 degree is more stable. Stability order, if you see, 1 degree is more stable than 2 degree, than 3 degree, and this is the stability order. Even free radical, if you take, free radical is having a carbon free radical or a general alkyl free radical. If you take, the free radicals are considered as a general example for the free radical. You take methyl free radical, let us take. So now if you count the number of electrons, 3 bonds into 2, that is 6 electrons are there, and this is 1, 7 electrons. To the octet system, 1 electron is less. So 1 electron less to octet. Less to octet. So therefore it is electron deficient system. Electron deficient system. So therefore, once again, just like the carbocation stability, 3 degree will be more stable than 2 degree, than 1 degree, than the only CH3 free radical. Okay, because it is the deficiency, the more the alkyl groups, the alkyl group attached to CH2 is more stable than the only CH3, isn't it? Because it is deficiency is there. Only thing is, which is more deficiency, means definitely that is positive charge is more deficiency than this free radical. That is charge wise it is neutral, however, but the number of electrons, if you count, valency electrons are there 4, but the octet, if you see, consider 1 electron is less, it is a 7 electron system. So 1 electron less to the octet, therefore it is electron deficient, therefore 3 degree, 2 degree, 1 degree. So carbocations and the free radicals will have same 3 degree, 2 degree, 1 degree, whereas carbanions is reverse. 1 degree is more stable than 2 degree and the 3 degree. So if you, these 3 intermediates, if you are thorough with the stability, the same thing we are going to find in the other different types of the reactions and observations, where we can apply this stability of the intermediate species in the coming reactions.